Hello, this video I will introduce the paper Improving Transformer World Models for Data Efficient Data. This paper was published at ICLR 2025, and its goal is to improve the sample efficiency of reinforcement learning using transformer-based world models. The main question of the paper is, can a better transformer world model help an agent learn from fewer real environment interactions? The paper evaluate this question on CraftText Classic. CraftText Classic is the 2D open-ended reinforcement learning benchmark inspired by Minecraft. The agent only observes a limited local view, and it needs survival, exploration, resource collection, and long-term planning. The answers of the paper is yes. On CraftX Classic, the proposed method achieves strong performance with only 1 million environment steps. The starting point of this paper is the sample efficiency problem in reinforcement learning. In CraftX Classic, the agent must explore, collect resources, and make long-term plans. However, the paper focuses on a limited setting with only 1 million environment steps. So instead of training only from real environment interactions, the agent also learns from image and experience generated by a world model. In this sense, the world model acts as a learned simulator that provides additional training experience for the agent. This is the overall training pipeline of this paper. The first step is the collect data from the environment. The agent interacts with CraftX Classic and gathers real trajectories consisting of observations, actions, reward, and done signals. The second step is to update the policy using environment data. So the policy first learns from the real experience. The third step is to update the world model. At this stage, each observation image is divided into patches, and each patch is converted into a discrete token. The transformer world model is then trained to predict future tokens, rewards, and done signals. The final step is to update the policy using image and data. Once the world model is trained, it generates image neural routes, and the policy is further improved using this image and experience. So the core idea of the paper is not to rely only on real experience, but to improve sample efficiency by learning from both real and image and experience. The main contribution of this paper can be summarized as three design choices. The first one is dynamic warm-up. If image routes are used too early, the policy may run from inaccurate virtual experience. So the paper uses image and data only after a warm-up period. The second one is the nearest neighbor tokenizer. It converts image patches into stable discrete tokens, making future prediction easier for the transformer. The third one is block teaching forcing. Instead of predicting future tokens one by one, the model predicts the tokens of the next time step trader as a block. This helps the model generate more consistent future states. Finally, let's look at the results. The final MBR agent achieves 69.66% reward on CryptX Classic after only 1 million environment steps. This is higher than Dreamer VC, which achieves 53.2%, and also higher than the reported human expert performance on 65%. Figure on the right shows that this improvement comes from adding several components step by step. So the main point is not just using a transformer as a world model. The important part is the stable design, including warm-up tokenization and block teaching forcing. To summarize, This paper uses the world model as a learned simulator for the agent. By combining real experience with imagined experience, the agent can learn strong policy from pure real environment interactions. That's all. Thanks for watching.